This is a production of Cornell University.
This is really going to be like a little storytelling up here. It's going to be a little bit about the evolution of our thinking around decision support tools and data science and how we've gotten into all of this work. But it's also going to be a little bit of me just getting up on a pedestal and talking about where I think we're going with precision and sustainable agriculture, because historically these concepts have been pretty mutually exclusive, right? We have teams of people focusing on precision ag, well, I'll get into that, precision ag, and folks focusing on sustainable ag issues, but not so much putting those together. So the talk today is just going to be what does that look like, putting that together, and how do we get there? I mean, and obviously, how do we get there in the face of this grand challenge, right? We've got to feed all these people. We got all this more food we got to produce. We got to do this in all of the face of these destabilizing factors, right? Like variable climates, competing water demands, herbicide-resistant weeds, declining soil and water quality. So we have all these challenges coming at the same time when we've got to escalate up our food production. And so how do we get there? And certainly, I guess I keep facing the wrong direction here. Certainly, precision agriculture has been seen as one of the ways that we get there. I like this image that I found on the web from Mosaic, and it just highlights, a lot around variable rate nutrient applications. But in precision agriculture as a whole, right, we focus on variable rate crop populations, nutrients, weed management, irrigation. Those have been the primary focus of what we've done in precision agriculture. And we've been doing this for decades now. I mean, it's starting to ramp up. The technology is getting there, and the adoption in the landscape is getting there. But we've been working on this for decades. So there is a lot of momentum in this area, and the primary focus is certainly been about efficiencies, right? Sustainable agriculture, on the other hand, has not received as much adoption in many cases, but is certainly also part of the solution for addressing these destabilizing factors in agriculture and helping us meet the grand challenge of feeding doubling food needs. And so those strategies in sustainable agriculture are old and true, and they've been around for a while, just a much less adoption for some of them, right? Cover crops, reduced tillage, crop rotation, organic agriculture, integrated pest management. And we have a lot of experience with this kind of stuff at Beltsville as well. So these are just some of the long-term cropping systems experiments at Beltsville that we're managing that are part of the LTAR network. And so they all feature these types of sustainable ag strategies. I'm in the Sustainable Ag Systems Lab, so we think about these kinds of things all the time. But there really hasn't, as I said, been this marriage between precision agriculture and sustainable agriculture. And I think one of the reasons sustainable agriculture, a lot of these strategies are not broadly adopted, is because it's very information intensive, right? There's a lot of knowledge that we need for these, and they're very site specific. They really respond to their environments, right? They're messy. They're biological tools. Everything matters. Cover crops are a plant, just like our cash crop. If you've got good fertility, low fertility, wet spots, dry spots, all of that drives the performance of that cover crop. And so we think that one of the ways that will increase adoption of these sustainable ag strategies is marrying precision agriculture with sustainable agriculture so that we can provide the kind of site-specific solutions we need to address these food needs. So let's use cover crops as a case study. We have a lot of experience with cover crops. We do a lot of work with cover crops. So while this concept of precision sustainable agriculture and what we're doing in this arena applies to a broad spectrum of different sustainable ag strategies, I'm going to focus on cover crops as kind of a case study. And so most of you, I think, are familiar with cover crops and that they provide a range of different services, right? And when we think about cover crops and the benefits that we get from cover crops, we know that it's largely driven by this biomass, how much quantity and how much quality we have. And so sure, this is just a visual depiction of services and benefits. This is not quantitative. But I think this is pretty accurate, right? You get a little bit of biomass in the landscape, you're going to get a little bit of erosion benefit. Get a little bit more, you start to affect water quality, infiltration, and the more biomass and the higher quality we get, we start to influence things like affecting the amount of nitrogen going into our cash crop and weed suppression and overall soil health. And so this is just, again, just a visual way of thinking about the value of cover crops. What are we trying to do with cover crops, right? Maximize profitability, improve production efficiencies, but there's also these other services that we're trying to do, and we're trying to do this in the face of climate change and all these other challenges in agriculture, and certainly cover crops, these multifunctional tools can play a role in mitigating all of these. Now, so let's take a transition now, and I don't want you to focus on all of these different data and the results in these data. I want you to focus on the kind of research that we do, right? This is a place-based study, right? This is a couple of years of research at Beltsville that I did, and a couple projects where we developed response surface analysis around cover crop mixtures and monocultures affect biomass production, decomposition and nitrogen release, water infiltration and storage, and greenhouse gas flux. And so these are interesting, and this provides a lot of value about how management comes together to affect service at a given space at a given time. But that's pretty limited, right? It's interesting at Beltsville in those fields in those years. And what we can infer from that is pretty limited. It gives us some insights around the system, but it's challenging to really be able to give site-specific solutions. And so the next couple examples I'm giving is all about how do we build site-specific solutions for growers by uniting precision and sustainable ag practices. So sure, longitudinal studies also provide a lot of value. ARS is invested in that. This is the LTAR network all across the US and different sites that are part of that LTAR network. We've got a bunch of those sites, and this gives us all sorts of insights about the longitudinal relationships that go on in the landscape, right? So this is ARS location Tom Casper in Iowa, and looking at this really shows that over time, the difference between with and without cover crops, how that affects nitrate leaching in the system. So how much nitrogen are we retaining? And clearly, time matters, right? There's all sorts of fluctuations between year, and the degree of benefit we get of with and without cover crop is affected and changes over time. So that's one of the reasons we create all these LTARs, right? Is to be able to have these time series studies, be able to extract what's going on in the soil over time and how these relationships happen temporally. But again, this is still limited. It's a very place-based study. It's done at a single location, a single set of soils. So how much can we infer from that? Here's another location site at Beltsville. So these are two LTARs. This is one that has organic and conventional systems in it. And here in a 2-year and a 3-year organic system, you can see how much hairy veg biomass we produced over the years. So the big thing that stands out is in this 2-year rotation, this orange, that's a corn soybean rotation. It's harder to get a legume established in a 2-year rotation. Whereas when we have wheat, we have better opportunities to get a hairy veg cover crop established. So there are many years where we had failure to establish or huge differences in overall biomass. And what does that look like over time? You could see big differences in the amount of nitrogen going into that system between those two rotations. So again, this is just me reiterating the same concepts. Time, space matters, and we can have a lot of information about a single location, but how does this transfer out to the landscape, and what can we do with this, and how do we build this into a precision ag scope? So we started to do this kind of work. We do have a lot of these kind of regional studies now where we're looking at across a latitudinal gradient. We're looking at cover crop performance and nitrogen and other services. And this was a neat study that we did a couple of years ago. And all of a sudden now when we look over space and time, we see some really interesting things pop out, right? If you were just looking at Maryland across these hairy vetch seeding rates, different planting dates, and different termination dates, there's a lot of noise in here, but the big things that stand out is that if you're looking at Maryland alone, that's going to tell us some interesting information about seeding rates and planting dates and termination dates for farmers. But when we look across this landscape now, we can see, wow, if you're in Massachusetts, you got to put out more seed and you get less biomass. So the overall cost of working with the cover crop is much higher. So where is it profitable to work with legumes across this space? When we start to look at these kinds of questions, it gives us more information. But again, this is still limited and it's regional. And we have other studies going on right now that's in motion looking at starter and side dress rates and sites all over the country. And we're working with Corinne here at Cornell. She might be in the room somewhere. There she is. All right, great. So, and we love these kinds of studies because they help us put together a little bit more about time and space and help understand how these things interact. so that we can create that information about how climate, soil, and management intersect to drive performance. And we're also trying to look more broadly and look at this at broader landscape. So this is an integrated weed management team funded by a USDA-ARS funded project. And we have a lot of different things we're looking at around addressing herbicide resistance. But I was just going to highlight this one experiment. We're looking at the interactions between cover crops and herbicides. And so we have these different cereal rye termination dates, different herbicide programs, different metrics. Again, you can see where I'm going with this. I'm not going to go into great detail on all those metrics. But here's cereal rye biomass now across the north central, south central, and mid-Atlantic US for 2 years. This now allows us to get even dialed in closer, right? These are more regions. We're going to be doing this over a 4-year period. So we'll have 40 to 45 site years of data across the US on how cover crops and herbicides intersect to affect cover crop performance and then also weed suppression. And here's just a little teaser. And this is where we start to learn some really interesting things. We've been looking at Chuck Muller's work and John Teasdale's work for a long time now and citing these threshold levels of biomass that we need to suppress weeds. And sure, in the mid-Atlantic, it's pretty clear you need a lot of rye biomass to impact weeds. But just look at how the difference between these relationships of rye biomass on weeds in the north central and south central. This was really shocking to me, that they don't need nearly as much cover crop biomass to get some of the same levels of suppression. And we're in the early phases of this, so I'm not looking too deeply into these results. But again, this illustrates the point that when we do these site-based studies and our data are not connected, we're not linking our information together across regions, we're not able to get this kinds of information and compile this in a way that we can see how these relationships work across different climate and soil and management regimes. And so the synthesis here is that these sustainable ag strategies are messy. They're super messy. They're biological tools. They respond to their environment. So you're going to have as much spatial variability between me and Tony as you will between me and a mile down the road with a lot of these sustainable ag strategies. That might be an extreme case example, but you get the point, is that they vary. They're messy. And so how are we going to get farmers to adopt messy tools that are difficult to manage, difficult to make prescriptions around, and then put that into a precision ag context? And that's where we think we need to go. And so certainly ARS and others have been promoting this GEMS model. We need to be able to link genetics, environment, management, and the social aspects to be able to provide a lot of those solutions. I highlighted what long-term research and component research can do, but I think that this all needs to be integrated with also on-farm networks. And we need to really greatly expand our on-farm networks. Many of us who've been doing on-farm research for many years have had lots of, struggled doing on-farm research, right? It's a lot, the common rule of thumb amongst many of my colleagues is that it works 40% of the time, that you have a lot of problems succeeding doing on-farm research and getting the good data. And so I think a lot of that has to do with just how you set up the experiments and the nature of the measurements you're doing. And we've had a lot of degree of success in the experiment I'm going to highlight, but that's also because we're asking so little of the farmer and there's very little treatments involved. And so anyway, we're big proponents of linking the LTARs with the component with on-farm research. So to get at the genetics, we built this national consortium of cover crop breeding. We've had a bunch of funded projects over the years through OREI, NIFA, and FAR to create legume, grass, and brassica breeding program. And we're a diffuse network across the country. So this is what we think about when we think about the genetics aspect of this, right? Is that we're not thinking about developing a hairy vetch line in Beltsville and everybody should use that line. We need site-specific material, regionally adapted lines. And so we created this diffuse network. Cornell, Matt Ryan's a big component. Lori Drinkwater is a big component of this team. But we have sites all over the country. We're doing on-station participatory breeding. We have breeders across the country, and we're doing selection and screening all across the country. And we've built this partnership with the plant material centers, these little drops here that represent NRCS plant material centers, because they're a diffuse network across the country as well that allows for all that advanced line testing and be able to create regionally adapted lines. So this is kind of how we're trying to tackle the genetic aspect of that. So here's our on-farm research team. We've been building this up over the last 3 years. We actually have some more sites in the Virginia area and further south, but we're going from Pennsylvania all the way down into Alabama and now a few sites into Florida, where we started at about 60 farms per year, and now we're at about 100 farms per year. And the only treatment out on this farm is with and without cover crops. That's it. So we don't control what the farmer plants. We don't control what cover crops they use. We don't control their herbicide programs, nothing. The only thing we say is we're working with you if you're a cover cropper, because we don't want to learn how to plant cover crops. We want to work with those who know what they're doing. And we want to then just either spray out a strip or not plant a strip of cover crop the size of their equipment. So these are often 120-foot wide or 90-foot spray booms. And so we have big fields across the whole field with cover crops. And you can see without cover crops, and that's what that looks like across these different farms. And so, and what are we measuring? We're measuring the nitrogen contributions of the cover crop. So we're monitoring its decomposition kinetics, its nitrogen release. We're doing full water budgets. So we're monitoring water infiltration and storage and availability through depth structured sensors throughout the soil profile, as well as humidity sensors, because we feel like there's a lot of work that needs to be done around refining how cover crops decompose and release nutrients. And also because of all of our process-based models are affected by these surface residues. That affects the whole hydrological cycles. So this whole team involves, climate science specialists, hydrologists, agronomists, soil scientists, and we have a whole social science team, which I'll talk about what the social science team is doing, and data scientists and computer scientists, because we're also taking adaptive decision support tools like our nitrogen release tool that came out of the Georgia group. We're developing water tools, and we're interacting with a number of the NRCS's cover crop tools that have already come out. And so this is to help both calibrate and validate tools, but also work directly with the farmers to give them information. And so here's just some pictures of what that looks like. We're doing deep soil cores in the spring and in the fall and the spring. So we're also looking at nutrient dynamics and flows in the soil. Here's where these bags go before they plant. So we take them from a spot, we spray out a little strip on the edge here, we keep them here, they plant, we put them right back into their fields so we can monitor decomposition dynamics and then release. So these are just what some of the sites look like. And we learned the hard way how fast we got to build towers here to get the solar panels up above the corn. And so lots of nuance. We've learned so much over the years because we basically buy the sensors out of the box. We basically used all open source hardware to construct the data flow of this. Because if you went to Campbell Scientific, you're looking at a $12,000 to $15,000 operation per farm. We get this down to about $2,500 per farm. That's why we've been able to scale this up and do so many farms, because we've constructed some of this hardware, and then a company really liked what we constructed, and so they bought this product now and are fabricating this whole data flow system of gateways and nodes, so and the cellular capacity of linking to our computers, so all that data is coming out of the field in real time. And so this is kind of my thinking around how we move precision and sustainable agriculture together, right? It's these regional and national projects. It's uniting cover crop council teams that we're doing right now as well, building on farm networks, and also the kind of diffuse networks of breeding. We put that together, then we can get to the point where we're building national products, but site-specific in their recommendations. And so this is a schematic that came out of a recent grant that we just submitted that articulates kind of our thinking and the theory behind this, right? And so we're trying to build an information ecology for precision sustainable agriculture. So that's uniting regional groups of researchers for past, current, and future research, and building the national distributed knowledge commons necessary, right? We have to move away from all this siloed data, these 2-year, 3-year projects that graduate students do where this went up and this went down, and it's really interesting and valuable, but it's limited in what we can infer and make, and how the kinds of tools we can make is how do we connect ourselves to a broader group. And so it's making these nationally distributed commons and using that information to inform decision support tools, refine existing tools, build new tools, and then farmers are using these tools, and simultaneously, as you saw, we're monitoring what's going on farm. So we're monitoring with all sorts of different sensors, with equipment-mounted sensors, drones, satellites, and ground-deployed sensors. And so we're capturing that information on farm. That's feeding back into our national data commons, and that's what creates that positive feedback loop, right? Farmers are using the tools are getting improved by the data as the data continuously improves, and we get that positive feedback loop. And so this is really what we're trying to advocate for, and what we're doing at a smaller microcosm now with our East Coast on-farm monitoring group and data science team. But we're also working with a lot of private sector folks and public sector grants to kind of build the whole national team. And NRCS has been really a leader in helping us do this. They've been funding data scientists in our lab to help unite the councils, as well as uniting regional decision tools that have been made already or that are in the process of being finished. And so we have some of those products, and I'll mention that in a second. But there's these key information challenges. And I come back to this siloed data. There's a lack of integration across our systems and our scales. Our data is not communicating with each other. So it's really cool the work Matt's doing here. But if Matt's work is operating in a bubble, it's cool for New York in that space and time. And how do we expand the inference of that? How do we connect that to a broader set of relationships where Matt might do a really good job at defining the functional space of data in his systems, but once that's connected to a broader ecosystem, then we can really link the climate, soil, and management, and our tools will reflect that. And so we got to break down and have open access, common data formats, community standards. All these things go into the kinds of databases that are necessary to do this. We're also dealing with a disconnected ecosystem of data, models, and tools. So I was listening to this great podcast the other day on Freakonomics about Trader Joe and why it's so successful. Has anybody heard that? Okay, nobody heard that. And so they talked about how they've designed choice and how consumers experience things and purchase things. And there was all this really good social science literature that was mentioned in there about how we really struggle with choice. Like if we have too much choice, we shut down and make no choices. But we want choice because we want that freedom, right? We want to feel like we have a choice. So if we go to buy something, we want there to be choice. But if there's too much choice, we don't buy anything. Like if you go down to the Jersey Shore and there's that wall of hot spices, right? There's like 100 different hot sauces. You don't end up buying any of them because you're like, I don't know what to do with that. But if there was like 6 of them, you'd probably buy 3. And so that's kind of the social science theory behind that. And that's what we're dealing with now with our farmers. It's the same thing. They're getting flooded with all these different tools. The tools are not communicating with each other, all these different platforms and operating systems. And this is just creating a glut. And it's making it very difficult for folks to make decisions or even like to take that next step to engage these products. And so we're really focused around addressing that. And so we've started with our first, what I learned in the data science world is called an MVP. That's not Tom Brady, but it's a minimal viable product apparently in the tech world. And so that's what we're doing right now. And so NRCS is helping to support us in our data science team where we're taking species selection, cover crop species selection tool, a seeding rate tool that's been developed by one of the plant materials centers, Paul Celan, who many of you know, and an economics tool. So these decision tools already exist and they're operational, but they're not communicating. So we're building a platform and we're actually at the finishing line of this. We basically spent a year and a half working with undergrads in the computer science department at University of Maryland and say, can you just break this 1,000 times? And so the students was just hammering away, all these senior computer science students, figuring out all the ways to make it not work. Once we figured out the tech stack and the ways that it needs to work, we spec that out, and now we're handing that off to a developer who's just going to finish this off in the next couple of months. And we have a platform now where a farmer georeferences their location, where they are in space and time. They might have some objectives, but then immediately says, okay, based on this, here's your species recommendation. And oh, that species recommendation is communicating directly with a seeding rate calculator, which is also directly interacting with an economic calculator. And oh, by the way, we're right now in the finishing stages of some of these products. We have a nutrient nitrogen calculator that's already getting linked up with these. So all of these will be a one-stop shop for all of these types of questions, and farmers can interact with this space. The last part of this, which I had no idea because I'm a nerd, right? I'm a scientist. I don't think about like how people interact with data and tools, is that these tools need to speak to the user. So there's a whole disciplines in the social science and data science world that we need human-centered design products. That us people who collect the data, we don't really do a good job at conceiving about how others use data. We're good at like, okay, yeah, I need this data to do this. So since I need it to do this, I need this module to do that so it all flows. But from a user standpoint, a lot of the public don't interact with and interface with things like that. So you need to have this human-centered design component going into the ecosystem of tools you're generating. And so our team has hired social scientists and data scientists who are doing just that. They're doing all the beta testing with farmers and customizing the interface and the exchange with the farmers so that it meets the way they engage with technology. How am I doing for time? Oh yeah, all right, good. So let's go back to this on-farm monitoring bit, because one of the things that's become clear to me in doing all this on-farm research is that how our information comes in and how our information goes out is not just important to us as researchers, right? We're interested in asking the what-if questions, right? So all this data is pouring in, and our crop modelers have all these process-based models, and the climate models are looking at how that performs in these current climate conditions versus future climate scenarios. And that's really great for these what-if questions and us talking to each other and writing papers to each other. But the farming community is interested in their own data. In fact, they don't really like to play with you very long unless they see their data right away, or they get bored. You know, we're just like flies on the wall in their room, and they're going to get annoyed with these flies pretty quickly unless they see results right away. And so it became crystal clear to us that it's not just from a research standpoint that we're collecting data on farm, but there's this whole farmer-facing component to this that our tools have to be doing, and that farmer-facing products is the opportunity for the co-learning with farmers, so that not only are they involved and not only are they interested in the results, but they're seeing it happen in space and time. So we started to develop this. We have very ugly interfaces right now, so they're terrible. But I'm showing you prototype 1, I'm going to show you prototype 2, and we brought in more data scientists to fix this horribleness. But this is where we started, right? It's like we're using our Shiny apps where basically in real time, as water data comes in, farmers can manipulate this so they can adjust which sensors they want to look at, which fields they're looking at, what time period, and then they can see the water dynamics in their field of with and without cover crop. We're now starting to develop like gas tank gauges, right? And more user-friendly imaging things where so a farmer can go out in the field and they see, that's my cover crop, that's my no cover crop. Is there water stress out there? Is there not water stress out there? That corn looks a little wilted, that one doesn't. Is that real? Oh wait, let me look. They get on their app, they type in their last name or whatever, and immediately they see, oh yeah, there is a difference in the water availability and the water budgets during this growing season. And so it makes that experience where they value the sustainable ag strategy more. Okay, cover crops matter. It's not this researcher wasting my time and making me do these strip tiles, you know? And so that co-learning is a big part of that. So the farmer-facing products have to improve. We're getting a little bit better. This is still horrible, I know. But so this is, but these are all happening in real time. So our databases interact with this and do these real-time analytics. So this is providing them biomass information. They type in their name, it gives them the fields they're cooperating on and how much biomass they produce. It lets them see where they fit in the spectrum of other farmers in that state. So it creates that kind of competitive, like, well, maybe I should be doing better. You know, if they think more biomass is better. And then it gives them the nitrogen release patterns coming out of our models. So there's models underpinning all of this, but what that interface is, I know this is terrible, but we're getting better. We'll have soil water as well, crop corn yield, so they can click on these different tabs. And there's all sorts of playing in this space that they'll be able to do that we're at that stage of things. So a lot of this stuff that we've been doing, we got really excited about, and so we started sharing what we're doing with others, and that got some interest from some private partners. So over the last year, that big SASCAP proposal that we submitted, all around that information ecology I shared, Esri got very interested in what we're doing in there, as well as Microsoft. And so we've been interacting with Esri and Microsoft because they're very motivated around the products that are being used in USDA and beyond, of course. But a big part of what we're trying to do is link government services like certification and cost share, where farmers have to go and engage government products, right? They have to go for their cost share on cover crops. Well, why shouldn't there be decision tools linked to right where they are? When they go to get their cost share, oh, here's the decision tool around cover crops, making the recommendations that they need that underpins the science that goes into those cost shares. So we started a pilot project with Esri and Microsoft. It's just really kind of a showcase what our team, the on-farm team is called Crown. And don't ask me what that means because I forget every time. Something cover crop and real time. USDA universities, Noble Research, National Wildlife Federation, several other groups. And so part of what we're trying to do is certainly leverage interagency data sharing and build geoinformatic platforms. That's part of this. That's not part of the pilot, but that's kind of necessary. And then we have a suite of different landscape tools that are used to validate and calibrate our models. And then we need to obviously take these tools and link them to these government services. And so that's part of where we're trying to go with this pilot. And then link that obviously to the amount of pipeline of products and tools that growers need. And so I took a photo from your work, Harold, because this is what Adaptive N is doing, right? And it's making adaptive nitrogen management decisions in the landscape to get improved nitrogen applications. And so that is a precision ag at its finest. And how do we layer in sustainable ag strategies into that? So how does this story play out when this whole field has a cover crop across it? So how do we modify these variable rate applications of nitrogen? So what our pilot is looking at is working with this on-farm data sets that we're collecting about cover crop decomposition, and nitrogen release and availability, and say, okay, we want to be able to do that, but we want that to link with precision ag technology like variable rate applicators, but we need to know how does the cover crops modify that. And so we're working with Esri and Microsoft as this pilot project to develop that. So through spatial mapping of the cover crop's performance earlier on in the spring, when we know it's at its maximum spatial variance, we can get a unitless measure of just spatial variance in the landscape, right? Just what is the distribution of performance, whether that's NDVI or other, and we're using other as well. But so let's just think of NDVI. Once we know what that spatial variance is, we could go to a farmer and we'd say, okay, here's the highest point in your field and here's the lowest point in your field. We're going to get through our sampling tool, it's going to georeference that for you and show you where to go in the field. And all you got to do is pull two samples, that high point and that low point. And then we analyze that material for quality and quantity. And then we can immediately put an attribute to that field. And instead of this being something unitless, now we have a distribution of the quality and the quantity of the cover crop across this entire field. And that's when we can start to link to the kinds of things that Harold has been doing with precision nitrogen applications and linking precision technology with sustainable ag strategies like cover crops that we know are messy as sin. And I liked this is just like, I think this is one of my last slides. I like this summary slide. I got this from Nick and Esri as we've been developing this and working with Esri and Microsoft to figure out what this looks like. This is us down here, right? We do all this kind of stuff. We collect data, we measure things, we might do some analysis. This is the scientific community, this is academia, right? Even some of the private sector, these things we do. And when this information is put into the cloud and it's interacting in these spaces and with these tools, it allows us to do the things I talked about today, right? It allows us to have products that are serving policy. In my case, this is national program staff, right? National program leaders need information to make decisions, to inform Congress about what's going on in the agency and beyond. But this, you can certainly see that this has other implications besides just USDA national program leaders. But then it's also these real-time apps for the scientific community for learning and also for farmers to make decision-making, and where we also are doing these real-time analytics. So we have farmer-facing products that are helping them co-learn. It's farmer-facing products that are doing real-time analysis. And then it's the research that us as scientists are doing when we build these databases. So anyway, I just like this schematic. So I think it illustrates some of the concepts I talked about today. And then obviously the next steps is not just having all that precise knowledge, but then doing the precision ag applications. And so there's lots of tech that's coming. It's really exciting time right now. This is some weed robots that are coming out. This is a group in Illinois that has already fully developed robots that are working well. They're really good for phenomics work. So we're looking to bring some of this into our breeding programs because it's really good for doing all sort of this real-time phenomics. But they're also developing hardware that attaches to this for other types of applications. And I think where the science now is on all of this technology is just, what does this army of bees need to be, right? We know that it's probably unsustainable for us to continue to think about $750,000 combines. That the bigger is just a really difficult model to sustain. Whereas if we can create a modular system where we build tools that can just scale, right? So if you're a 50-acre farm or if you're a 10,000-acre farm, if everything's scalable, then it just becomes how many units that you put out into the landscape that's swarming across those fields. But those units also need to be like, how big does it need to be so it gets from one end of the field to the other with a certain product, whether it's a liquid or whether it's a solid, a grain. So all of that, I think, is where the robotics and the science and a lot of the tech teams are at. And so it's a really exciting time. It's a really exciting time.
I think we have about 10 minutes for questions. I have one right now. Can you just say a little bit about what you're thinking about? You're interfacing with government programs and taking these tools. You know, in the past conversations, that sounded really interesting. And it seems like you might have an advantage over some other people out there. Doing this for advice.
Maybe, I don't know. Yeah. So the question is talk more about government services, and then is it because I'm with the feds that we're trying to do that? I don't know. I mean, we're excited about this, and we've been interacting with some of the different agencies and private sector folks around what that might look like. USDA certainly doesn't shy away with working with the private sector, certainly know that. But I don't know whether it's just because I'm in government. I mean, the whole team that I'm doing this with, the vast majority of the team is universities, right? We're up and down all over the place, and so it's mostly universities. But this idea we're really excited about is just how do we merge these? And since we're already collectively, the cover crop councils working with NRCS, I mean, all of the regional cover crop councils are receiving some financial support and cooperation around the project management, data sharing, and decision tools. And so I see this as kind of all of us are doing this, but I think NRCS is really motivated around this, and whether or not this becomes just NRCS or can we get this USDA wide? Like I mean, just dreaming, like imagine if the risk management agency had kind of these products linked to them, right? And so they're using tools that scientific community made around cover crops and how that affects water. That would be cool. Is that going to happen? I have no idea. That's what the purpose of the pilot is to showcase things that can be done and hope that there's reception around that.
I wondered about economics. You didn't mention much about that, but in farmer choices, it's much about what are the costs and benefits of switching. Maybe I'm already growing a cover crop. I hear about that there's a better one, but how much is that seed versus this, and how long does it take for that to kick in? So are you doing that now, or is it a way for that kind of stuff to link into this support platform you're talking about?
So right off the bat, our MVP with NRCS is in cover crops, a seeding rate, a species selection tool, and economic calculator. So those tools are already built. All we're doing is getting them to communicate, and we're practically to the finish line on that. And then we have project managers in the councils regionalizing the information in those tools. And so that's happening. And I guess what
already have that in there, have it embedded.
Yeah, it's in there. And my attitude around economics, and again, let's just narrow the scope down to just cover crops, right? Because there's a million scenarios here as we scale up to different concepts or practices. I mean, the economics associated cover crops is a very complicated affair. We need to, we constantly get into this prescription-based mentality, like, well, does it increase my yields? Well, where do you live? It's like if you live in Iowa, if you live in Florida, Texas, or Maryland, the role of a cover crop, the species we use, all of that matters. And so we can't really be thinking in terms of just single numbers or single objectives or simple economics. We create the space that ideally the motivated farmers can then investigate that space and see how that plays out for them. So instead of giving prescription, we say, here's the space, go and play, go figure that out. And sure, and that fits with the kinds of tools we want to generate, because we're trying to develop scalable tools, right? So that some farmer's going to get into this tool and they're going to just be like, all I want is just like the simplest concepts to just understand this. And so it's just going to be very user-friendly for the entry-level farmer who's not very techy. But we want our products, and this is part of what we're trying to do with these products, is then all to go all the way up to the farmer who's doing like variable rate applications on, and doing that on the fly and has that tech built into their systems. So you want tools that are expandable knowledge-wise for the user. And so some will probe and ask those economic questions, some will just look for light engagement, and others will actually be making decisions based on the tools. Next question.
Follow-up, are you collecting data on how farmers are making decisions based on these tools, like in your design process?
So the question is, are we making, are we adjusting our tools and the way they're used based on farmer input?
Or just like getting feedback on like how the farmers are actually using the tools and what kind of decisions they made with them?
So we have a whole team of social scientists involved in the project, and they're doing just that, from the human-centered design aspects to working with the farmers and doing annual surveys and interactions, and then there's all this wish I knew the language they use. They always use all these special terms. They're doing all these kind of like beta testing or whatever it is with them in person with the products, and so that's informing the development and the design, but it's also helping us learn about what their needs are. And so there's a whole suite of kind of social science aspects to that we're just at the front end of. Ann.
Thank you for the presentation. I think sustainable ag and precision ag and the combination is a really interesting avenue. When I think about sustainable agriculture, I think about diverse, complex ag landscapes. And when I think about precision tools, or tools used in precision ag, I think about these tools having been developed in very simplified ag landscapes. So my question for you is, what difficulties have you had regarding calibration in more complex ag systems?
Yeah. So the question is, how do we calibrate our tools for more complex systems, right? So we've got a perfect answer for you. I mean, it's going to relate to cover crops. Surprise, surprise.
Yeah.
So we know that all quality is not created equal. So when we started working around cover crops, we were just thinking about carbon to nitrogen ratios, right? And some of the results that came out of that work, Jeff, was that probably it's more than just carbon and nitrogen that's driving dynamics. And so we became pretty clear that we need to be working with like forage quality assays, right? So cellulose, lignin, hemicellulose, and I didn't present any of that data today, but we did extensive assays on the quality of this material. We already have a nitrogen release model that estimates how that cover crop decomposes and releases nitrogen. We're then getting hundreds and hundreds, like when this study's over, we'll have like 600 site years of data on cover crop decomposition and nitrogen release over time. So we get biomass decomposition and nutrient release. So we've got the climate, we've got the soil, we've got the quality and the management, and then we basically are building out the models to reflect that, calibrating and validating the models while simultaneously also doing incubation studies where we're creating controlled moisture regimes, temperature regimes, and other conditions to look at how does dew affect cover crop decomposition, right? We know that actually a big part of what drives surface decomposition now of cover crops is just dew. There's a lot of water in dew, and that's what's actually keeping the cover crops wet and decomposing. And so the surface conditions is extremely explosive, right? It's like hot as heck, it's cold as heck, it's dry, it's wet. The surface conditions are changing daily. So that's part of what we do is get at that. So we see this as linking the process-based modeling, the empirical data collection, the incubation chambers, and then the field testing, and then the tools. So it all is concerted together, and then hopefully when it's all done, it'll fit your standards. That's the question.
So there's a lot of variability in the field, which is what precision ag is trying to do. And you have this $2,500 set of instruments that you're putting out in one place in the field. And that's what you have the ability to do on each farm. And can you share with us how you decide or how you use that tool set to capture that small scale variability? Or how do you lend the information you get to small scale variability?
Yeah, that's a great question. That's a great question. All right. So the question is, how do we deal with small scale variability? And because in the end, we still don't have sensors every foot out in that field, right? And so that's impossible. I mean, the very fact that we have hundreds of farms and sensors and the amount of depth structure sensors is an achievement in itself for the team. We're blown away that we pulled that off. And so we're expanding some of the sensors out there. So we do have 2 replicates out there per farm, and we are trying to get spatial variability. We are trying to go into different slopes, different performance of the covers. So we are capturing kind of 2 points across the landscape in there. Obviously, other metrics like cover crop biomass or yield or crop populations are measured at different scales than decomposition and water. But we're tracking all of that, right? So we georeference all those points, and this is the antithesis of how my first 10 years of my career was, right? Or 20 years, whatever it is with grad school as well. It's like where we control everything, and then we got one little variable we tweak and say, okay, we can say a lot about that, right? Now we're just taking the shotgun approach, right? Let's like get out there, let's measure as much as we can, as many sites as possible, and that if we get 500-600 site years of data, and then we have those sensors at 2 locations, now we have 1,000 points in the landscape and a lot of attributes that we're measuring to those points. And the hope is that will get us there. But simultaneously, I mean, I spend less of my time thinking about this data than I do how do we get more money to get more sites. So that's what I'm constantly doing is just, how do we shake the trees? How do we move this out further, more states, more sites, the Midwest? And so that's been a big emphasis, just how to move the on-farm monitoring, because the more sites, the more that we can get at that. Yeah.
Other questions? No? Let's thank Stephen.
This has been a production of Cornell University, on the web at cornell.edu.